Okay, hi everyone. First of all, happy Independence Day. I just realized it's 15th August. Yeah, and a short introduction. I am Vaibhav Sharma. I used to be an MSc physics student in ITB like 2 years ago, and with Dushyant, we like sort of wrote some stuff on the blog you might have seen. And since then, I've been here in US. I've been doing my PhD in physics in Cornell University for the past 2 years. Yeah, and so I'll just this is some work that I did. This is my first work that I did here in my PhD, and we earlier this year we published this work, so like this is done, and so I'm just going to be presenting this to you. And I've kept it pretty light in the sense that I've not put too many equations, or because I didn't know everyone's background, right? Somebody might have different backgrounds, so that's why I thought let's keep it pretty general. So I've tried to do that. And despite that, if you have any questions, just feel free to like, even in the middle of the talk, just feel free to stop and ask. And yeah, it would be better, I guess. Otherwise, I would just feel like I'm just talking to myself on the screen. So whenever you have a question or you think something is not clear, something is wrong, just like stop me and be like, okay, well, what's happening here? And even at the end, we can have some time for questions and discussion. And maybe I can discuss why I chose this field and things like that. So yeah, just feel free to stop whenever you have questions. All right, so what I'm going to discuss is as the title says, Bose-Einstein condensation in a non-equilibrium setting. That's just a lot of words, but we'll come to everything one by one. So equilibrium studies, we often study systems in equilibrium, which is just fine. But equilibrium systems, as you know, are sort of studied by using, rules of thermodynamics or statistical mechanics, and you have this steady state, and that's the stuff you study usually. But non-equilibrium can be very interesting. And non-equilibrium, most importantly, has dynamics. So things evolve in time. You're not in a steady state. You go towards a steady state. And it's more of how a system reaches equilibrium or reaches stability, which is the important question once you are in a non-steady state or non-equilibrium. And if you think about where are these non-equilibrium systems in the world, it's all around us. If you look at that, the universe is still evolving, right? So the universe itself is probably not in equilibrium, it's still evolving and going to some steady state, which you probably don't know. And if you think about experiments in the labs, they often start out in an initial state, which is not in equilibrium. And then in the experiments, you see the system evolves and does something and then goes to equilibrium. So what we are studying here, so this project that I did, we studied bosons. And just a reminder to everyone, bosons are particles with integer spin. And the key property of bosons is that they can all occupy the same state. And at very low temperature, the bosons have this very interesting quantum state where at super low temperatures, all the bosons, they sort of flock together and enter the ground state. And that's called the Bose-Einstein condensate, or I'll just refer to it as BEC in short. That's the Bose-Einstein condensate, which was predicted back in 1920s or 30s. And just as an example to show you, if you have, say, a system of bosons, you have this energy versus K graph. K is, you can call these different quantum numbers of the different possible quantum numbers of bosons. And you have this energy diagram where K equals 0 is the lowest energy. And as you go to higher Ks, you get higher and higher energies. And at very low temperatures, Bose-Einstein condensation is just that all the bosons occupy this low energy state. And that's just the Bose-Einstein condensation. And the question that we will ask now is, what if this Bose-Einstein condensate, this BEC, is kicked out of this ground state? So the non-equilibrium setting I'm talking about is you take this BEC, which is at the ground state, normal stuff, you kick it out of the ground state, and then what happens then? And so that's the dynamics we want to study. And we find out that some non-obvious things happen. It's probably not as obvious as we thought it would be. It's that we saw some unique phenomena which are interesting. And then another question you can ask is why do you want to kick a BEC out of equilibrium? It was happy there. Why do you even want to do this process? What use is that? And there's multiple ways to think about it, but I took an example from like the early universe, which is I thought is cool. That's an example to just show why non-equilibrium studies are really important or can be really important. And so this is just an example. This is not the work I did, but this is just to motivate that why non-equilibrium BEC or Bose-Einstein condensation is interesting. And so if you think about the early universe, and Some of you might have heard that there's this Higgs field, the Higgs boson, which was discovered in 2012 at LHC. And the Higgs boson apparently is the particle that gives all the particles their mass. And so this Higgs field pervades all space, and it did so in the early universe as well. And the Higgs boson, the particle associated with that is the Higgs boson, and that the Higgs field gives the mass to all the particles like electrons and protons and whatever. So in the very early universe, it is theorized that the Higgs field has this potential V, and this phi is the wave function of the Higgs field. And in the very early universe, which was very hot, so the temperature was really high, the V versus the wave function, which is the phi graph, looked like this. And the minima was at phi equals 0. And so the Higgs field, all the Higgs bosons, they formed a condensate at phi equals 0. In equilibrium in a very hot universe, all fine. And so the Higgs bosons condensed at that. And when the Higgs field was at this phi equals 0 point, this equilibrium point, there was no mass of the electrons. So that was the very early universe. All the particles were massless. But then what happens is that the universe starts to expand, or things happen, and it starts to cool down gradually. And as it cools down, there's a phase transition in the Higgs field. So again, it's theorized that what happens is that the Higgs potential suddenly changes shape like this. So it becomes a double well because there are these two wells. But the Higgs boson didn't know that. So it was still stuck here because this phase transition happened suddenly as the temperature cooled down, and suddenly it's now not at the minimum energy. It's not at the ground state. It is in a non-equilibrium state because it's at a higher energy. And there are two new ground states that it will go to. And so then what happens? And so we now know today, we have observed the Higgs boson, and our theory says that the Higgs field is actually now at this state, which is the new ground state, which is at phi not equal to 0. And this phi not equal to 0 is important because the fact that the Higgs field has a non-zero value in vacuum, that gives mass to the particles. So basically, the whole point of this, to show this, is that the Higgs field at some point must have been here, and today it's here. And the question is, how did this happen? So this was like a full Bose-Einstein condensate. Higgs bosons are also just bosons. So this condensate somehow from here got to here, which is the new ground state. And that's the non-equilibrium kind of setting we are thinking about, and that's the question we're asking, that how does this happen? Right, so the question is, how did the Higgs boson go from phi equals 0 to phi equals non-zero? And there's a wrong idea that seems obvious, but you might think about that. Okay, the Higgs field, the condensate was here, and it just rolled down the hill and reached here, which just seems a very simple idea. And like, why not? It's like rolling down in a gravity potential, you just like roll down a ramp or roll down a hill. But that's a wrong idea. That idea is incorrect, and the reason is that a rolling down the hill implies that this Bose-Einstein condensate was a Bose-Einstein condensate in every intermediate roll down the hill, but every intermediate field value, it remained a condensate, which is true for like a ball, but it's not true for a quantum state like a Bose-Einstein condensate. That's an idea that's often used because no one sometimes cares to study deeply, but that's a wrong idea. And so what we do is that we study in general how, if you have a Bose-Einstein condensate in this sort of a non-equilibrium setting, how does it come to a steady state? What are the time scales, and really what happens? And so that's what we're going to do. And again, as a note, it's not that we're studying Higgs bosons. This is just a motivating example. What we do is, in general, we just study bosons, which can be atoms, which can be anything. And then we have a setting which we imagine in which we do this problem. But the general features still remain the same. Okay, so our system, what we study. So what we envision studying is that we have this. I'll come to this lattice first, maybe. We envision this setting, which is an experimental setting. This can be done in experiments, so at least you can test these ideas, and they have been tested. So you have this kind of a lattice that you build with lasers, and I can come to how you can build a lattice with lasers and stuff with this field later on. But you can imagine there is this one-dimensional lattice, and this has this peculiar structure. There are alternate sites are higher in energy as compared to let's say the even numbered sites are lower in energy, and the odd number sites are higher in energy. This is also called a double well lattice, or a bipartite lattice. That's just words. But the important thing is that there are some lower energy sites and there are some higher energy sites. And what this does in this E versus K picture, and I've denoted Kx because we are considering this lattice in the X direction, is that you have two bands in general. This lower band is when particles fill this lower energy sites, and you have this higher band where the particles fill these higher energy sites. And the kx is just particle momentum in the x direction. This is the quantum mechanical momentum. And if you solve this problem of energy structure using a lattice, those are details maybe you can see in the paper. What you find is that for the lower band, for the lower energy sites, the kx equals 0 is the lowest energy state. But if you notice in the higher band is flipped. And so for the higher band, the kx equals 0 energy state is actually the highest. But doesn't matter. You start with this sort of an experimental setting and you load your bosons, which can be even atoms which are bosonic. So like, for example, lithium 7 atoms are bosonic. They have even numbers of like neutrons, protons, and electrons. And you load it in this lowest energy state, you cool it down, and you find that it's a Bose-Einstein condensate at this kx equals 0, lowest energy state of the lowest band, equilibrium, steady state. Very nice. And what you can do is that then you can give it a kick. And what you do is that you sort of give it an energy kick. So you don't change the momentum, but you only change the energy. Again, this is stuff that can be done in experiments. So like, just trust me, that can be done. And so you give it this energy kick, but not a momentum kick. And so what happens is that it suddenly occupies this, this energy, which is the highest energy in the higher band, which is a deeply non-equilibrium setting. And you just gave it a sudden input of energy. And this is kind of like the Higgs case I discussed, where the Higgs was on this sort of a hill, and there's a high energy state that was not in equilibrium. And it's pretty similar to that. The picture is slightly different, but the general features again remain. And what we study is that what happens after that. What are the dynamics once you do this kick? And so to study that, what we do is that we imagine that we say that there are interactions between bosons, which is true. And the form of interactions we consider is the simplest case. And the point here is that can we come up with the simplest possible theory to just account for the observed effects? So we consider the simplest possible interaction, which is two bosons come in with energy E1 and E2, momentum K1 and K2, and they collide, scatter off each other, and go into energies E3 and E4, momentum K3 and K4. And so the scattering is called 2 in, 2 out. And you just have energy conservation. So input energy is equal to output energy, and your momentum conservation. Input momentum equals to output momentum. Okay. So the simplest possible setting, imagine. And the initial state is that all bosons are in this K equals 0 state. So that's an initial condition, initial energy. And then you sort of turn on the scattering and you say, okay, let's turn on the scattering. They start colliding. They all have high energies. And what happens after that? And so the scattering starts, and this energy and momentum through these scatterings begin to redistribute. Okay, high energy particles collide, and maybe more low energy particles arise. A bunch of things happen. And in short, what we find is that this condensate, it breaks up. This condensate breaks up, it evaporates in some sense, if you think about it as a liquid. And that's what we observe at first. And the technique used here, just to mention, is we only used quantum scattering, using scattering terms like that, which is like 2 in and 2 out scattering, and Fermi's golden rule to calculate the rates of different processes. So that's pretty much all we did. And again, details, if you want, you can read from the paper, but I've not added here. Otherwise, it would have been, not that good. So the picture we find is that as you evolve in time, as you solve these rate equations, you let the scattering happen. You observe that in the higher band, the Bose-Einstein condensate evaporates. So what happens is that this was a condensate here, and it just, all the atoms or all the bosons just spread across the higher band. So and there's no more a condensate. A condensate implies that all the bosons occupy a single, and this is not what happens. All the bosons just scatter and just fill the entire higher band. There's no condensation at one energy point. And yeah, and you can ask where is the energy, right? So if you think about it, all the bosons started here at this high energy state. And now I claim that the energy gets redistributed here. But remember, my process conserved energy. If all the energy was here, how are there more particles with like lower energies? And the subtlety I didn't mention is that we envisioned this lattice in the x direction, but in the y and z, the bosons were free. They were free to move. Which means that there's additional avenues for energy, which is in the y and z, this expression you might have seen. which is in Y and Z, they can have momentum Ky and Kz, and that's the quantum mechanical formula for energy associated with that. So what they can do is that they can fall down from here to here in Kx. So they lower their energy in Kx, but they can balance it out by increasing the energy in Ky and Kz. So energy is conserved, and yet you find that this Bose-Einstein condensate evaporates and fills this higher band in the Kx. And so this is against the idea of rolling down the hill. The condensate doesn't roll down the hill. It actually just breaks up, it evaporates. And then you evolve it for more time. you keep evolving your equations in time, and you see what happens. And then the behavior changes. So it had evaporated at this time. And then later time, once you wait long enough, you see that it recondenses. So the Bose-Einstein condensate forms again. And it forms again in both these two places, which are the lowest energies within the higher band. And so you notice that this is a Bose-Einstein condensate, which is not at the K equals 0 point. It's a non-zero K, which means the Bose-Einstein condensate has overall a finite momentum, which is also special. And it's still not the lowest possible energy of the system, but it's the lowest in the highest band. So it's still kind of a non-equilibrium BEC, but it's still a BEC. And it did come down from the hill. It did not roll down, but that's the phenomena we observe. And the Bose-Einstein condensate at this point is stable for a long time. The problem is that there's this gap in the band, and turns out that interactions can put you eventually in this band, but that happens at a longer time scale. This gap sort of forbids it. And in the equations, you can see that the rate of processes happening within the higher band are much faster than the rate of processes which take you from here to here. Eventually, if you wait long enough in a lab, you'll see that this Bose-Einstein condensate ultimately goes here. But this is sort of a pentastable state, stable for a long, long time. And so there's a new Bose-Einstein condensate in this higher band, and it's sort of in a metastable equilibrium. And there was no rolling down the hill. That was the idea we were trying to explore. That does it just roll down the hill? And it's not. It first evaporates and then recondenses. And then the question you can ask is, what time does it take? Or how does the time scale with the parameters in the problem? So we find there are two, in general, you can say there are two time scales. One is what we call the evaporation time. So that is the time when you start off with this condensate, and then you say, okay, how long does it take to evaporate? And we find that this evaporation time depends on the strength of interactions. A thing I didn't mention is that we perform our calculation in a weak interaction limit. So the interactions are weak, and you can imagine a possible idea as you can consider strong interactions, and that we have that. And maybe the physics can change, but we consider weak interactions. And the idea, what we found is that as you increase the strength of interactions, what happens is that this condensate is more spread out in some sense because the particles are interacting so much. The initial Bose-Einstein condensate, which was at the highest energy state, that's more spread out. And so you have these slower collisions, and the time taken is longer. So as the interactions are sort of weaker, you actually have a faster evaporation time. And there's the other time scale, which is recondensation, which is that once you evaporate it, you ask the question, okay, how much time does it take to recondense? And that we found just only depends on the number of bosons. So as you increase the number of bosons, there's faster recondensation, and intuitively you can just imagine that if there are more bosons, they collide more strongly, there's just faster processes, and just things happen on a quicker scale. So so it was nice, sort of makes intuitive sense about what happens and why does it happen. So we calculate these time scales, and they sort of agree. Yeah, so that was pretty much what we did. We studied in this project, and we just put out the paper and done. Yeah, so the punchline here was that this higher band or non-equilibrium physics is interesting. There can be weird phenomena. There can be wrong ideas, which might sound intuitive, but they're not correct. And there are other avenues in this in these kind of systems. So you have these lattice systems, or these materials, or anything pretty much you consider which has energy bands. So higher band physics is interesting, and there are other avenues that can be explored here. So for example, I talked about bosons in the higher bands. I was talking all about bosons, but you can ask, what if you have fermions in the higher bands? And fermions, maybe you can have superconductivity in higher bands. It's a question. People have thought about it, but I don't think it has been seen experimentally that well. So it's a good idea to study that. And then obviously you can ask questions: what happens what happens if the bosons in a higher band are strongly interacting? If the interactions are too strong, does the physics change? How does the physics change? Those are questions we haven't answered, but maybe someone else can. And there's a lot of other interesting stuff here. And I'm just giving this. This is not a link. This is a. This is just I've written the number of my paper, so you can just put this number in Google. You can get this, or this is the archive number. Archive is free to access. It's probably this is the better thing. And like I sort of like this field. Like people do weird creative stuff in this field. Like I don't know if you've heard that. So, for example, Hawking radiation from a real black hole has not been observed, and probably would never be. It's super weak for a massive black hole. But these cold atom people, they often build these sonic black holes, which is like a real black hole. You know, light cannot escape. They create the sonic black holes, which means sound cannot escape. And it's often just a Bose-Einstein condensate, which is sort of big enough. And there's things about it has some event horizon past which excitations don't go. There's analogs of that. And people study that and they sort of map it to black holes. There's stuff they do that way. Yeah, and there's people who think about these dark matter halos in the galaxies. And if dark matter is a boson, and then again, in a cold galaxy or in a cold universe, this halo is a Bose-Einstein condensate, so you can map that. There's tons of weird stuff you can do, and just any field you just put your hand and just try to simulate here. And even in experiments to do that. Or if you're interested about materials, then again, optical lattices are clean. So if there's real material, electron-electron interactions often cannot dominate because it's just phonons or ions or whatever. But in the cold atoms, in an artificial lattice, you can just kill all the unwanted processes and you can engineer whatever you want. Like a nice field to explore. Yeah, let me come to my last slide, which is what research do I do? So I do what is often called either ultra cold or ultra quantum matter research, and I do theory. I don't do experiments, but you can do experiments which are really fun. And the thing here is that we pretty much study anything in the deep quantum regime. And why I like this field is that you can study almost any phenomena in the quantum regime. Like it's not restricted to any material, it's not restricted to any particular system, any particular star or galaxy. It's just very general. Even in a project, I just mentioned bosons, and bosons, they can be Higgs bosons, they can be atoms, they can be photons. It almost sometimes doesn't matter. And everything in the world is either fermions or bosons, or in this case it's neither. But and you can just study those phenomena in general in this field, in the quantum regime. There's no restriction to any material or any type of physics, and you can explore a lot of things in this field. Like you can explore neutron stars, which in our picture you can imagine is just a bunch of neutrons, which are just fermions, which are very strongly interacting and closely packed together. So you can study neutron stars. You can study superconductivity, which is electrons forming these pairs, and superconducting, which is again electrons or fermions. So you can do that. Topological physics. You can study quark. People study quark-gluon plasma as some general, things of particles interacting or whatnot. You can do all that. And I think we discussed this optical lattice when I was asked this question of how do you do this experimentally. An optical lattice is great because you always study in like solid state physics and stuff that the real materials like copper or whatever, they have this lattice, and which is true. But the thing in these real materials is that the physics is very complicated in a real material, because in a real material there's so many other things going on. There's imperfections, there's phonons, and whatnot. And so sometimes interesting phenomena, they just get hidden or it's very hard to study. But an optical lattice is an artificial lattice. And the good thing about an artificial lattice is that it's perfect. There's no defects in an artificial lattice because you made it with a laser. There's no phonons because there's no ions or atoms which are vibrating. So any interesting phenomena that's happening just because of like interactions or just because of the particles there, they don't get hidden because there's this external fluff that is there in real materials which are complicated, dislocations, effects. It's just not there. So that's why I find this field very interesting. It's very clean, and like you can just dial down to the most important phenomena instead of being just lost in this jungle of the real world, which is very complicated. That was just my 5-minute pitch of the kind of research I do. And if you're interested, this research is awesome. And you can also do experimental in this, and that's equally interesting and great. something.
I have a question.
Yeah, go ahead.
So can you go back to the previous page?
Mm-hmm.
So when the potential changes, why is that the before the transition? Why is the Bose-Einstein condensate still in that the upper position? The
Yeah.
middle
So what
phi
happens?
equal to 0?
So it's in quantum mechanics, you will often hear this word. It's called the sudden transition. And sudden transition means it means that if the transition is very sudden, it's not gradual. Your quantum state doesn't have time to follow the new ground state. It's just happens so suddenly that's just still stuck there. If the transition happens on a slower time scale, then that's what you call an adiabatic transition. And then as the potential changes, you follow the ground state. But the transition has to be slower. And phase transitions typically are fast and just sudden.
Okay, yeah, thank you.
How exactly did the transition take place if it did not roll down? Well, the transition transition was independent of the bosons. Transition took place as the temperature cooled, and the physics of that is different. We can maybe discuss it at the end. But it's just that as the transition happened suddenly, the condensate was just, all the bosons were stuck there because it happened just suddenly. They had no time to react in some sense.
Vaibhav, I have a question.
Mm-hmm.
So when you mention that bosons are interacting weakly or strongly, what does that exactly mean? I mean, how do you quantify an interaction essentially?
Good question. If we come back to the diagram here, it's probably easier. Right, so the obvious energy scale here is, you can imagine this width of the band, which is called the bandwidth. So you can imagine what are the possible energies it can take within a band, and that's called the bandwidth. And so weak interactions would mean that your interaction energies are smaller than the bandwidth. So a weak interaction cannot suddenly take you here. It's smaller than the bandwidth. You need more processes to actually make it cover the bandwidth. Is that clear?
Yeah.
Mm-hmm. Yeah, feel free to ask me anything. I mean, about the project.
Vaibhav?
Yeah.
Hello? Question?
Yeah.
Yeah, can we just go back to the same slide which was open?
Mm-hmm.
Yeah, this one. Here you mentioned that first we created the condensate in the lower band and then we kick it in the upper band, right?
Mm-hmm.
But we are changing the energy, but we are not changing the moment as a part.
Mm-hmm.
So my question is, how do we do this experimentally? I mean, this sounds like a very non-trivial task. How one does it experimentally?
Okay. Yeah, it's a good question. So how is it done? I don't know if you have heard about optical lattices. Do you have?
No, I haven't.
Okay. So optical lattice, as it sounds, is this weird thing where you create a lattice with a laser. And the way to think about it is that if you shine two lasers, two opposite lasers, you can imagine one is of the same frequency, but in the opposite direction, you get what are called standing waves, which you might have studied. Two they interfere and they form a standing wave. And the standing wave is just the standing wave where the electric field intensity oscillates. And you can have multiple, and what this lattice is essentially is that you have these two lasers of slightly different frequencies at slightly different angles, and what you get, the standing wave pattern you get is this. You can create these standing wave patterns with the laser. And remember that the laser intensity goes as the electric field squared. And so as the standing wave has this oscillating electric field amplitude, the energy at different points in space is also different because it goes as E squared. And so if you have an oscillating amplitude of the standing wave, so it's not a traveling wave, you have the E square also oscillates. And so what the bosons see is that they see that you have these, in space, you have this is like energy versus space diagram. So they see that the electric field amplitude is the lowest here, is highest here, lowest here, highest here. And so you can imagine that they would want to settle in the lowest state. So what they do is that they settle here. And this is exactly the potential that they see. That's just because the laser electric field intensity is the lowest here. They want to settle there. Now you ask, how do you do that kick? So if you imagine that they've all settled in this lowest energy state, which is in this momentum space is the Bose-Einstein condensate here. What they do is a subtle thing that they suddenly change the phase of these lasers. And what happens is that you can imagine this pattern suddenly moves to the left. And that's a sudden transition, happens at a very fast time scale. And as this pattern moves to the left, this boson didn't know what's happening. So it's still stuck there. But suddenly, it's not in this, but it's here. Because this pattern suddenly moved to the left, and all the bosons suddenly find themselves in this, what I call the odd number sites, which are the higher band sites. And they still had the momentum k equals 0. There was no time to change it, but their energy changed because they're suddenly now occupying the higher field levels. And that's how you do it. You just move the pattern. And you can just do that by changing the phase of the laser and stuff. Did that make sense?
Yeah, it is. Thanks.
Hi, Vaibhav. So I joined a little bit late, so maybe I'm misinterpreting. So when you explain the optical lattice, so basically this happens in an optical lattice, or you are studying in an optical lattice. So is there any scope for it happening in a real material, real lattice?
Well, one problem is that in a real material, what you have, the degrees of freedom, or what you have is electrons, which are fermions. So then there's no Bose-Einstein condensation for fermions. So that's probably the answer, that in a real material, you only have electrons, which is
Right. So it's a purely theoretical study.
Yeah, but like I mentioned in the motivation, the early universe had a bunch of bosons, like I was mentioning about the Higgs boson. And yeah, so phenomena like that, yeah, then those are bosons. And then you can imagine forming potentials like that. And in particle physics zoo, there are plenty of bosons. There are mesons, which are bosons, or whatnot. But yeah, in a real material, there are no bosons, unfortunately. But in the universe, there might be.
Right. Thanks.
I have a question. So yeah, in this slide, you mentioned that fermions in higher bands can display superconductivity. Is that proven?
Okay, so in the lower band, they definitely do become superconducting as you cool down, and which is fine, which is what happens even in a real material. And when we talk about fermions, we can even talk about real materials. It's a good thing. Right. So when you cool down fermions or electrons enough, they form these Cooper pairs and they become superconducting in the lower band, which is fine. But in the higher band is, from what I know, is still an open question. And in the higher band, I think there have been experiments which have tried, and in this field, which is ultra-cold lattice, which is optical lattices, because in a real material, again, if you go to the higher band, there's just so many other things that happen in a real material that you sometimes just cannot see the real physics. There's always phonons which mess you up sometimes. There's always imperfections. But in an optical lattice, I think it's still not been proven that it's still not been shown that you have superconductivity in the higher band. At least hasn't been shown experimentally. I think theoretically some people might have tried studying it, but yeah, experimentally hasn't been shown. But what I showed here, the thing I did, which is with bosons, that has been seen experimentally.
I wanted to ask, and the reason behind asking this is that can this kind of a study help us in finding that high TC superconductivity, like the cuprate superconductivity? Can this phenomena explain it? Higher band condensations in this way, or for the bosons, or high bands for the fermions?
Yeah, I mean that's a good point. Because it's somehow, you're right. I mean, there are some relations, because in a high temperature superconductor, you have these cuprates typically, and cuprates, they say there's these d orbitals, which are sort of higher orbitals, and there's this orbital band physics which is happening. It's one I don't know, and I don't think anyone has a good answer of what happens there. But yeah, you're right. I mean, these things, and that's part of the motivation why you want to do these non-equilibrium things, or these higher band things, because the lower band physics, everybody knows it, has been seen experimentally, has been done, and you're right, it doesn't explain high temperature superconductors. Yeah, this study, it's not that it can directly solve the problem, because not that the cuprates are exactly like that. But yeah, once you solve these kind of problems, you do get ideas and hints what physics might be. Yeah, it could be useful.
Yeah. So in this direction, I mean, for the ultra cold gas, if you do an experiment of an ultra cold gas, and you're trying to simulate real material, essential part of the essential motivation is to do this. There are phenomenon that depend on the disorder in the system. For example, if we take Hall effect, so that depends on the plateaus depend on disorder. Is there a way an extremely controlled experiment like an ultra cold gas experiment can simulate disorder?
Yes, which is amazing. They can, and in fact, it's often done. You're right. There's disorder in quantum Hall, and there's I don't know if you heard about many body localization, but that's also some interesting phenomena, and that also hinges on disorder. Many body localization is sort of you have electrons which localize at some point spontaneously, and that needs disorder. And what they do is that they form these nice optical lattices, and experimentally there's ways to sort of randomly shift energies of each side. Just disorder. Disorder is just a random energy shift at each side, and they can do that. I'm not sure exactly how, but it's very common, is what I can say. Is often done, and many body localization, which is a phenomena that hinges on disorder, has only been observed, I think, in ultra cold atomic systems, not in a real liquid, because again,
Nice.
but yeah, disorder can be any disorder you can engineer.
Yeah. Thanks.
There's a lot of disturbance.
Yeah, I was asking about your PhD life. It's actually that few days or maybe a couple of months ago, I heard somebody that they decided directly from your post that they are dropping their plans for PhD. I mean, from your recent post. So I thought like I would like to inform you or like put some disclaimer or something regarding that, like what you intended to say.
Oh my God, I think we should take down that post. That was not the intention at all.
Yeah. I mean, the question is like, if you're like, was that all worth it? Like, would you do this again if you're given choice?
Yeah, I mean, I like physics. I like talking about it. Like, if you ask me to give a talk every week about some physics topic, I love to do that. I love talking. I love talking about physics, sharing physics. Like, if you ask me to do this every week, I can come up with different topics, not my own work. I'm happy to discuss it. Like, it's just that I love physics. And if you love physics, then I think a physics PhD is very rewarding. And the stuff I said in the post, I mean, that's the reality, right? PhD is hard. It's not going to be easy. If it's easy, it's probably doing something wrong. It cannot be easy, right? PhD is like you're doing new research, you're creating new stuff, and you're studying you're studying systems which haven't been studied by anyone else, right? A PhD is not like you have an answer at the back of the book and you'll just find it, or you know you're wrong. You often don't know you're wrong, and a lot of papers have mistakes and they're wrong, and they make wrong approximations. Like this paper we did weak interactions. You can question why not strong interactions. We did not answer that question. I don't know what the answer to that question is either. So PhD is hard. There's a lot of stuff to be learned, and as you go into a PhD, you realize there's so much you don't know. Like I came in, I had decent enough grades in my MSc, and I was like, I know a lot of stuff, and I just dropped when I saw like, oh my God, there's so much to learn. And like I used to go to talks, and a priori, or I would not understand anything. But you get through that, right? The important realization is that you realize there's stuff to be learned. There's stuff you don't know, and then you just shouldn't be afraid to ask questions. I think those are the two things. So I keep asking questions. My professor, my advisor, whenever I have meetings with him, I ask questions on the most basic of things, and then that's how I realize, oh, I don't know about this stuff. This is so basic, but I still don't know it. And then I go back. We have the internet, which is awesome. And I just look at some paper or something, and I just learn about it. And that's pretty much your PhD is about. It's a great place. You you get paid to learn, which is, I think, kind of amazing. But I think I do think that it's sort of it's a subject of passion. That if you really like physics, you will enjoy all this. You will enjoy learning. This is a rewarding experience. But yeah, if you don't really like physics, which is partly why you would do a master's and try research, because it can be frustrating too, and it's not for everyone, and which is fine. Everyone shouldn't do research. We have a lot of things to do in the world. And yeah, if you don't think it's great, then a PhD can be sort of depressing or devastating. But yeah, I think if you love the field, it's a very rewarding experience. And yeah, I can just talk all about physics. But yeah, that post was not meant to discourage. It's sort of just a reality check. Yeah, someone in the chat says, consider talking at various. We often do that actually. I mean, back here in the university, this journal club is a great idea, and we have stuff like that. And it's not that you only have to discuss your work. We sometimes just like pick up papers from others, or some recent papers, or old papers, or some physical phenomenon. Like, oh, well, what is this? And someone presents it, and then people discuss and ask questions. And yeah, if you do that, let me know. I can try my hand at it. I can attend. It was just sort of an update. Like, okay, 2 years of PhD I have completed, and what did I find or what happened? And I mean, I just wrote about real stuff. Like, okay, you go in, you have to. PhD's work, right? You have to find an advisor, you have to work, you have to learn so much stuff, and there's stuff you'd find difficult, and that's part of the PhD. I mean, PhD is you have to enter this. You are entering this world of this huge unknowns, and there's no one who goes into a PhD and knows everything. Otherwise, why would you need a PhD? But yeah, so it's hard, but it's rewarding. If you love physics, I'm pretty sure you'd find it amazing. I see Shine has asked a question. I don't know if he's still there, but he asked what are the courses one must take to go into ultra cold atoms in, say, masters.
Attend Pinaki, man. Sorry.
I think courses, no one offers an ultra cold atom course as such, but I think that I would say what you need to learn is quantum mechanics super well. So whatever quantum mechanics courses are there, the higher level, take all of them. And statistical mechanics. So those are the two basic things. And then if there's a condensed matter course, that would help a lot. But yeah, quantum mechanics and statistical mechanics, you should have a good command over it. That's pretty much the main thing. And field theory can help in the future, but that's not required. It just gives you an extra edge. But yeah, it's not required at all. But yeah, PhD is hard, but it's awesome. If you love physics, it's the short punchline. And yeah, you think you know a lot of things, but that's just not true. That's just never true ever. We always think we know a lot of things, but then somebody comes in and shows you the reality. A good rank in chess, jam, or whatever is not going to get through your MSc, and then a good grades in MSc, they will help you, of course, but they're not going to get you through the PhD. You have to put in the work, and yeah, you have to put in work in almost anything. Harshil is asking, how long does a PhD take in US on average? No, not 3 years, unfortunately. An average physics PhD in the US takes 6 years. And the reason is that there's a reason too. So you would notice that in Europe, for example, a PhD takes like 3 or 4 years. And the problem in US, well, not the problem, the way they do things is that US admits undergrads directly into PhD. So you would do your bachelor's and you directly can get admitted to a PhD, which means so a PhD program in US thinks that everybody who's coming is an undergrad. That's their assumption, which means the first 2 years, they want them to take courses and sort of do a master's. So every PhD program in the US is sort of in disguise integrated PhD program. And they expect everyone to do like coursework or, explore stuff for 2 years. And then after 2 years, the next 4 years are considered to be like pure PhD where you just do research. Doesn't mean that you can't start research in your first year. I did. But that's the way the program is structured, which means you won't get out before 6 years typically, unless you do something exciting. You get funding for the full 6 years. So I mean, Cornell guarantees you that you will be paid no matter what. You will be paid for 6 years. That is the guarantee that they give. But the interesting question is, how do you get paid? That's not a guarantee. So the thing here is that when you enter the program, every first year they TA, so they do a teaching assistant job, which I find really fun, and that's for like 10 to 15 hours a week. So you get paid for your first year by TAing, and then after that, if you have already chosen a professor, You sort of come under the ambit of the professor, and then if the professor has funding, they pay you. Life is simple. If the professor doesn't have funding, then what they do is that they say, okay, you'll have to TA for the rest of the PhD, but you will definitely get a TA position. It's not that you might not get it. You will 100% get it, but you have to TA. And a good example is high energy theorists, like people who do theoretical particle physics. They just don't get money. Their grants, I mean, yeah, they just don't get that much money. And so their students often have to TA, but they do, and it's fine. But everybody gets paid. My professor, so since I'm also in theory, and theory is less money usually. So my professor has some money, so he funds me alternate semesters. So the previous semester I was TAing, this semester I am being funded, the next semester I'll be TA again, and then it goes back and forth. And for TAing, I choose interesting courses, and yeah, if you like teaching, it's often fun. And if you're an experimentaler, you typically get funded all the time. Experimentalists have more money than theorists, usually. More often, almost every time.
I mean, when I said that there is no freedom in choosing the advisor, okay, that is a loose statement maybe. What I've observed, okay, I'll tell you the case that happened with me in IISc. I went for the interview in the condensation matter, the Department of Physics, and they said, they gave me a list of people, and they said you can choose whoever you want. Then I was put in the waiting list of the selection for the PhD, and they 3 months after the interview, I get a call that there is a professor who liked your interview, and if you want to join, you have to join him. There is no one else that will take you, because there are no positions available, and that is the case. And I have friends in IIT Madras and in IIT Kharagpur. The situation is that you join in the first 3 months of the course. The coursework is just 6 months. In that 6 months, you're supposed to do a project. In that project, who are the person you do the project with, they'll end up being your supervisor. Now, how it is a norm that you join that guy. Now the question is, what happens if you don't like him? Neither you can't go to someone else and you can explore again. You have to sign after 1 year, and you understand the situation, right? So it's kind of tough. So the DA institutes, the degree granting institution called HBNI, the Homi Bhabha National Institute, they have 7 places in India. They follow this culture that for the 1.5 year, you do projects with at least 2 different people, and you then decide at the end of 1.5 year whether you want to sign with someone else or you want to stick with that guy. That is one of the biggest freedoms that HRI offers in India. Not just HRI, all the DAE institutes, the so-called IMSE, TIFR, ICTS, yeah, and HRI. That's what I meant by not choosing an advisor.
I think there's a question for me from Rishan. Average funding grant or TA grant be sufficient enough to pay off student loans from masters? Yeah, the thing is, the money you get in your PhD varies a lot by what university you're in and what place is it in. Well, what place is it in determines your living costs. So whether your university is in New York City versus a small town in Georgia, it matters a lot. And honestly, I cannot give an answer of how much money you'll get paid and how much of it is enough. It can vary very wildly. It's very hard to give a number, and then depends on how much loan you have. But yeah, typical PhD grants are not, I mean, they are good enough for a single bachelor. But I think, for example, it's often said that if you have to like manage a family, tough. But for a bachelor, it's fine. But then again, you have a loan, how much, and yeah, that can be tricky. That's not an easy question to answer. was the transition from engineering to masters in physics? There's a lot of uncertainty. It's good that we have this blog, which is physics after engineering. I remember searching on Google and not finding anything. And until IIT Bombay accepted me, I was very worried that, I had left my engineering job. I'd got a job after college and I just left it. And I was like, if I don't get in IIT Bombay, I'd be in big trouble because I wouldn't have anything to do. Thankfully, I did. And I mean, in my engineering, I think the good thing that I did is that once I figured out that I like physics, at the very least, I tried to learn undergraduate level physics by myself and whatever online courses, MIT OCW or like books and stuff. And it's not like I was perfect. I learned everything, but I had, I would say, at least a rudimentary undergrad knowledge that when I went into masters, when I took the courses, I could understand the lectures and I could, you go back, do the homework, you practice, and then I could actually understand stuff. So I think my preparation in engineering did come very useful. And that way the transition was not bad, I would say. So yeah, at least at the undergrad level, some basic quantum mechanics, and you don't have to go to a very advanced level in engineering if you're doing a master's anyway. But yeah, those things help a lot, I would say.
Hi, this is a more general question about like PhD in general, and this is directed to you as well as to Ganesh. So oftentimes like I have just passed my BTech, and so often even when I was doing some research in BTech, so oftentimes it happens that you get a mental block, like you get stuck somewhere, or like you're not able to overcome it, or you feel like no, there's no way ahead or something like that. So how do you deal with such a situation, or has it ever happened to you guys?
Yeah, I mean, there's right. If when you start a project, right, you don't know what's going to happen. If you start a project and you know what's going to happen, it's not a project, right? It's what we call a homework. So
Yeah, it's true.
There is that unknown, and projects have dead ends. It's not uncommon, and I think a very important skill, which I think professors tend to have and we don't as students, is to identify when do you reach a dead end, and is to probably pre-identify which projects have probable dead ends. And I mean, for example, so I finished this project, right? And there's another project that's also kind of finished. But I'm working on new things now. And when we were trying to find new projects, we were discussing what we should do. And there were ideas we came up with. And in a week or two, we knew it was a dead end, or sort of we knew that, the calculation technique we'll use or the things we do, it hit a dead end. Maybe I tried a few things and it didn't work. And I think sometimes it's the advisor's role to sort of guide you and figure out that, okay, I don't think this is going to work out the way we're doing it. This is a dead end. Maybe we should move. So sometimes there's that, and the advisor helps a lot. I think at this point, the advisor is probably everything because I don't know anything. And so there's that. And sometimes projects have dead ends, but even with the dead end, once you reach the dead end, there's something that you did. There's something which is sort of publishable or something that you learned. And I think sometimes you can sort of pivot your project. You say, okay, we have reached this dead end, but there's this stuff that we have done. What if we take a slight turn and use this stuff to do this thing, which may not be very interesting, but at least it's something. So that work you put in, it's useful. So I think a good advisor would guide you well and would sort of make sure that they would either recognize the dead ends early on, or if you indeed reach a dead end, you can still salvage it. You can still make something out of it. And yeah, I think an advisor's role is huge because at this time, I don't have the necessary skill or experience to know that. Maybe in future I'll learn that. That's part of why you do a PhD. But yeah, an advisor is very important in these cases. And just talk to your advisor frequently. Having a good relationship with your advisor is, I think it would be a very happy PhD if you have a good relationship with your advisor.
Right. Thanks.
What would be the most important thing that to be a master's student would have to keep in mind, work towards in order to get into a good PhD program, say US or Germany? Right, so US and Europe are sort of two different beasts here. If I talk about US, for US PhD programs, I would say, well, there would be two important things. One is you have to have awesome grades in your core physics courses. That's what they look at, because physics GRE, let me tell you, is not looked at in the same respect. And I think at Cornell, we are talking about, there's been talks that they might just cancel the physics GRE and the GRE itself. They don't like it and it doesn't help much. So in future, you might not have the GRE at all. It means physics courses would take even greater importance. And so your grades in courses like quantum mechanics, statistical mechanics, electrodynamics, classical mechanics, those are the four big ones. You need good grades in that, and like say mathematical physics or some math course. And if you don't have good grades in that, that can hamper your chances because they would think that you don't have enough preparation. So one is that, ensure that you get good grades in that. I mean, it's okay if you don't get a good grade in one of them, but if you want to have a shot at something, get good grades in your master's in these courses. The other thing is letters of recommendation, which is the second most important thing, or maybe equally. And for that, I mean, you need 3 typically in US, and it's not easy to do research with 3 professors, but at least 2 you should try. So you should definitely try to do some research project with 2 professors in some field that you think you're interested in, and do an honest and sincere job. Right? It's not that you have to produce something and publish a paper. That's totally not a requirement for a PhD. What is important is that you're honest to yourself, you do some good work, you work hard. And if you do that, then your advisor would notice that you worked hard, you're sincere, you tried your best. And if the results come, awesome. If they don't, you still get a solid recommendation that this student I worked with was hardworking, sincere, learned fast, and like was awesome. And then if you have 2 solid recommendations, maybe a third one can come from a course professor. Ideally, everyone should be from research, but it's not always possible. But you would be fine if you have 2 solid research recommendations and 1 maybe a course recommendation or whatever. For the US, I think those are the 2 most important things. And of course, applying in universities where, you have to pick the universities where the field you are interested in, there are plenty of professors and good work being done. Because if they notice that your application says you want to do condensed matter physics and there's just not many people doing that in the university, you'd get rejected. So that, and Europe, I think, is different in the sense that Europe sort of expects master students. The thing I talked about US being made for bachelor students. So in Europe, it's like you go there and you start your PhD right then. You get an advisor, it's sort of like an Indian program, and you just run with it. Which means for European applications, you have to have a very clear idea of what exactly you want to do and which group you want to work with. And so I think research experience for Europe applications is really important. So the letters of recommendation is the most important thing. Of course, grades are important. They're never not important. But yeah, you have, so for example, I had a friend in ITB and he was great. He was an engineering student. He was an engineering physics student. And I remember he said he was done with courses. He was like, he told me that he like hated courses and he's no longer he doesn't want to do courses. So he said, US is out of the question. I'm not going to go to US for my PhD. So he only applied to European schools. And the good thing about that is the guy was awesome that he exactly knew which kind of research he wanted to do. So he applied to European universities in particular groups. So it was like, this professor, I want to work with this professor or this professor. And he got 4 or 5 offers. And he ultimately went to Germany to do his PhD with the professor he wanted. And he went there and started research. There was no coursework, nothing at all. So if that's what you want to do, and sometimes people are tired of courses after masters, you can do that. But then you won't have the freedom to choose an advisor. You have to choose an advisor in advance. They look at undergrad performances too. I think, well, they would look at the whole transcript, but I think if there's significant improvement in the masters, it probably overshadows the undergrad because, recent stuff matters the most, I would say. What should we consider deciding whether to do PhD, India, abroad, interest in astrophysics? So from what I know, or what I've been told, in India for astrophysics at least, Ayuka is great. I've only heard good things about Ayuka. And I think, I don't know what exact field you are interested in, that whether Ayuka is great in that, but anyone I know who's been to Ayuka, they say Ayuka is awesome. It's a great program. It's a nice small community. So it's not that you should just discard India as an option. But I think it's important to know what you want to study and at least in India, you can sort of ask around and see how the experience of the people is. And same for, I mean, I would say when you apply for a PhD, if possible, just apply everywhere. And then once you have the offers, then make the choice. Sometimes it's not viable financially, which then is another question. But if it's viable financially, just apply to any schools, any universities that you like, whether abroad or in India, and then make a choice later. And of course, staying in India means that you want to stay in India, close to your family, close to your friends, or whatever, in a familiar place, which changes the dynamics. But I would say you don't have to make that choice in advance. If you can apply, just apply everywhere and sort of delay that point of decision making to a few months later, and then think about it again. But yeah, it matters where you want to go. I guess another familiar question that I saw was being discussed is that, in the Indian setting, you essentially don't get much choice in advisor, while in the US you get a lot of choice. Yes, in the US you get a lot of choice, but it can be a double-edged sword, right? It's not that getting a choice always is not good. So for example, if you come into US and you start your program, say if you don't have a good idea what research you want to do, you're just exploring and sort of bouncing around like a ball in the room. Sometimes 2 years pass by, you didn't like 2-3 professors, or you didn't like anything, and you're kind of stuck. You had a lot of choice, but you just can't make a decision. And sometimes in life, it's often easier when the decision is made for you. You don't have to think. Sometimes when you get the opportunity to think, you just mess everything up. So this is one factor, which is that. The second thing can also be dangerous, is that in US sometimes, say I want to work with some Professor X. He's awesome, he or she is great, and that's the only professor I want to work with. But turns out there are other students in my program who got admitted with me, and they also want to work with Professor X. So there's like 4 students who are competing now. And the professor has limited money and limited time. So professor's like, I can just take 2 students. But remember, 2 students would lose out. And then you're like, okay, I didn't get into this professor's group. And turns out I don't much like other professors at all. And again, you're stuck. And in the Indian context, it was easy because you had sort of a guarantee, I guess, or in Europe, you definitely have a guarantee that you're going to work with some particular group. So in that way, it can be double-edged sword. I mean, everything has its pros and cons is what I want to say. Yeah, it depends on what you want or what you like. And yeah, I've seen here that there have been competition for positions sometimes in groups, and it's always because more students want to join and the professor is just one person. That can happen. It's not uncommon, I would say. I would say another thing I learned in my MSc is that when you get interested in physics initially, I don't know if I can say it for everyone, but you sort of always get introduced. You always get introduced using astrophysics. I think that's the one thing that often captures imagination. And I think if you see popular science programs on like Discovery or Nat Geo or whatever, I think astrophysics is the king, because I think it's the one thing that you can easily explain to people and get them excited. And I also thought that astrophysics is awesome, and that's what I want to do. But I think that stayed during my engineering as well. But when I went to MSc and at IITB, there were a lot of professors, and you can attend seminars and stuff, and you talk to other people, to talk to other professors, realize there are other professors. I think that's when you realize that there is a lot of things in physics, and depending on how much you like them, it's not that astrophysics is bad, but I mean, you limit yourself by thinking that physics is only astrophysics. Physics is a lot of things, and there's just tons of interesting stuff that people do that I did not even imagine that it's possible or it's even done. And I think an MSc, you can take it as an opportunity to at least explore their different fields. And you would find that sometimes you're skilled in one, like you're skilled in something that you didn't even know about. You may not have the skills to be a theoretical astrophysicist, but you may have skills in some other avenue. And you can only find that out if you explore, and you can be the best in that other thing, which is equally interesting and important. So there's just, tons of different kinds of physics, and it's a huge field out there to explore. And it's like astrophysics or theoretical particle physics, another common thing. Those are not just the only 2 things. And in MSc, I even did a project in astrophysics, and I honestly didn't like it that much. But yeah, there's just a lot of things to explore.